All right, welcome to Module 2. Now, in Module 2, this is going to be one of the shortest modules that we deal with because a lot of these things are just going to be really straightforward, things that we've talked about in the past or you've dealt with in previous courses. We're going to talk about collections, okay, and what collections are. I'm going to jump right into the textbook itself and talk about different collection types. There's 4 general categories when it comes to collections. There's linear. When we think about linear, let's look at it from the standpoint of a one-dimensional array. An array with length only. Okay. Or we could look at it as a list, but in this context, what we're going to deal with in here, let's talk about arrays. The second would be hierarchical, which would be trees. Graphs are similar to trees. We'll talk about that a little bit later. And then we've got unordered collections. Okay. Now let's go ahead and step forward and we'll go look at what a linear collection is. And we'll talk about what are we talking about when we say a collection. Now, a collection is a group of values. All right? It's a group of values. We have a linear collection, which has values D1, D2, D3, D4, D5. That is an algorithmic way of representing it. And algorithms, that's something that mathematicians use more than programmers. Programming initially came from mathematicians and accountants. But I digress. Let's focus on what we're dealing with. You may see things start numbering with 1. That's the algorithmic perspective. And programming, when we're in Python, we'll deal with things from 0 to 4. As long as we understand in our Python code, index 0 to length minus 1. In algorithms, 1 to length. Okay, so the length of this is 5, and algorithms, or a mathematician would start counting at 1 and go to the length. In programming, we're going from 0 to len minus 1. In either case, it's a one-dimensional group or collection, is the term we're going to use. Now, these may be ordered, but by default, we will look at this as an unordered linear collection. We have the ability to order it, but by default, we have the assumption that it is unordered unless, for whatever rule that comes into play, it could be ordered. And we talk a little bit about that in the next module. Okay. So, or might even talk about it a little bit in this one. So, things that are linear. A list is linear. A stack is linear. Now, when we think of stacks, the example they use in this chapter is a stack of dinner plates. You can't just grab, effectively, you can't grab a plate from the middle of the stack. Last in, first out. Keep that in mind. The last one added into the stack is the first one coming out of the stack. The one on the top is the last one added. The one on the top is the first one that comes out. And when we talk about stacks later, we'll talk about the verbiage of popping. I don't want to deal with it now. We'll just think of as last in, first out. It's like a stack of papers on your desk or a stack of plates in a cabinet. We've also got something else called a queue. And if any of us have been to Publix, you wait in line in the different checkouts. If there are people in front of you, that's a queue. It's an ordered queue. By default, the first person in line is the next person to get taken care of, and so on, and so on, and so on. The length of the queue. Right. So the first in is the first out of the queue, because we deal with things at the beginning of the queue. We don't interact with people at the end of the line, we interact with the people at the front of the line. So first in is the first out. That's in accounting we call FIFO, first in, first out. Now when we talked about a list or an array, that's a little bit different. So our lists and array, we have indexes I can pull from any point. Stack, last in, first out. Right? All those examples are linear. They're lines of values. Or I should say lines of objects, because what's in there are objects. They're data types, which essentially are objects. Now let's look at hierarchical collections. And these, we predominantly call them trees. And when we look at it, it's really upside down. But in this depiction, we say node D1 is the root of the tree. So if we say this is the root, if we rotated that and everything went up, then it's the root. And it's I like to call it more of a bush than a tree. Here's the root of the bush, and then here's a node, and here's a node, and from this node breaks off other nodes. The connection in between these nodes is called an edge. So we have the root node, the edge, and another node. This is the parent node and the child node. Parent node, child node. When we get here, this is the parent and these are the children. So when we think of it in the context of a family tree, here's the grandparent who had 2 children. One of those children had 3 children. Maybe that context will help you a little bit. Words to remember: root, parent, node, child, node. It's not a relationship per se, it's called an edge. Child as well as parent. It's a child to D1, it's a parent to D4 and D5 and D6. And what's in between D3 and D4 is an edge. Nodes, edges. Okay. So let's proceed. Those are hierarchical. There's a hierarchy to them. Now, when we get to graph collections, there is no hierarchy. Between node D1 and D3, neither of them is a parent nor a child. They are nodes with an edge between them. An edge being a connection. D1 and D2, there's an edge there. D2 and D3, there's an edge. So D2 is connected to D1 and D3. D4 is connected to D1 and D3. None of them are children, none of them are parents. These are just individual nodes and edges. Okay. We'll talk about them more in a future module. But these kind of come into play if we're talking about highways and the best pathway to get from one city to the next. There may be a cost associated with an edge, and we want to find the most efficient pathway to get from one node to another. And this may be an expensive edge, and these may be very inexpensive edges. Okay. So like I said, we'll talk about that more in the future. Here's an unordered collection. An unordered collection could be a bag. If I have a bag and I throw a bunch of marbles in it, it is a collection of marbles. There is no order to them. Just so happens that everything in there is a marble. Any bag that I have full of marbles, I can reach in and pull any of those marbles out, and they're just arbitrarily coming out. There's no specific order to them. And we'll talk more about bags in the future. Okay, so we have some collections are sorted and others are not. Now, some collections are naturally ordered. Let's say that I create a randomly generated list or a randomly generated array of numbers. They may not be in any specific order, or I could create an array of numbers from 0 to 5. Now that would be ordered. So depending on how it's created would effectively dictate whether it was sorted or not sorted. I don't want to assume that an item is sorted unless I know for a fact that it is sorted. Now, if it's not sorted, most of these things are very easily sorted. I've got the ability to use a built-in function to sort a list, but one of the things when it comes to a list gets kind of cumbersome because a list allows us to put a multitude of different data types within it. So we're storing more than just one data type. I want to add to this an array. We'll say a one-dimensional array. This graphic does not include add-ons like NumPy, and we'll use NumPy in this course. And NumPy allows us to have an array. And we can take that array and use a built-in sort function to sort that array, however we want it sorted, ascending or descending. All right. In the next module, in module 3, I'll talk about different ways of sorting, and we'll look at different sort algorithms and code for different sorting. We'll manually do sorts, and we'll also use sort functions. So we have a list, assume it's unordered, or we can make sure that it's sorted. A queue, assume there is no rhyme or reason, and somebody, let me differentiate between a queue and a priority queue. Now, a priority queue, the first one in line will be the one that is next. A standard queue could be like the line in Publix where, yes, we are standing in line, but there's no specific priority put on there. And somebody may say, you know what? You have less items than me. You move to the front. So for some reason, somebody gets moved to the front. So we'll talk more about that and get it all ironed out. Which one is a regular queue and which one's a priority queue. We'll deal with that more when we deal with queues. A stack, I discussed that. It's like a stack of dishes or a stack of papers. Last in, first out. A queue by default is first in, first out. String is an ordered collection, and they're not ordered by value, they're ordered by index. Now, they have to be in a particular order if it's a string of characters that represents somebody's name. So a string by default is ordered. Even though they're not ordered by value, they're ordered by index. We've got those unordered collections, a bag, a dictionary, and by default, these aren't necessarily ordered, but they can be. And then we've got sets. So bag, dictionary, and set we'll talk about towards the end of the course. So just want to go over the types of collections, whether they're linear, non-linear. Right. We've got hierarchical, so they say binary search tree, so a tree or a heap. And then we've got a graph collection, and we talked about that one that's non-linear as well. Okay. So that's overall what we deal with when we're talking about collections. Okay. I'm going to talk more about algorithms and dig into algorithms more at the start of Module 3. I don't want you to get confused or frustrated when it comes to algorithms. Algorithms are not that bad. We're not going to dig deep into them. There may be a concept or two that you're not familiar with when it comes to math that, yeah, I'll have to get you up to speed when it comes to, let's say, what logarithms are or what exponential means. There's things you should have dealt with in algebra, but may not have been well versed in. Like I said, mathematicians deal with algorithms more than programmers do, and mathematicians start counting at 1. Programmers start counting at 0. So that'll be a little cumbersome. We just got to remember, when we're talking about algorithms, we start with 1. When we're talking about programming, the index starts with 0. So make sure you go through, read the chapter, get familiar with the different data types. And within this module, I've got that last chart that I showed you that broke down the different types of collections. And then we'll have an algorithm exercise that I'll add a video to go along with it. That'll be next to it. That'll help you prepare for this algorithms exercise. I'll dig a little deeper into algorithms in that video. Okay. So on to the next.